Welcome to Dr. Tarazi's math site. What is a prime number?
A positive integer greater than 1 is a prime number, we just say prime, if its only positive factors are 1 and itself, which means it can only be divided by 1 and itself. Examples 2, 3, 5, 7, 13, there's a whole bunch of them.
What is a composite number?
A positive integer greater than 1 that is not a prime is a composite number, a composite. Examples 4, 15, 21. Now 15 can be divided by 3, by 5. 21 can be divided by 3, by 7.
Primes between 1 and 100.
Here are the 25 primes between 1 and 100.
Properties.
The only even prime is 2. 1 is neither a prime nor a composite. Except for 2, all primes are odd. Not every odd is prime. Here are counter examples. 15 is an odd number, but it's not a prime because it can be divided by 5 by 3. Same thing 21, 25. Other properties, even every integer n greater or equal than 2 has a prime factor. There are an infinite number of primes.
How do we find out if a given number is a prime or composite? Theorem.
This theorem is going to let me know how to find out if a number is a prime or not a prime. So if n has no prime factors less or equal than the floor function of square root of n, then n is a prime. Otherwise, it's a composite. This is the floor function of x, meaning the largest integer less or equal than x.
Recommendation.
To make the most of these videos, I suggest pausing the video when you see this button, solving the problem, and then resuming the video to check your answer.
Example 1.
Determine whether 253 is a prime or composite. Okay, we take the 253 square rooted, get 15.91. I'm rounding here. So now I need the floor function of 15.91. That is obviously 15, the largest integer, not exceeding this, okay? So now you list all the primes less or equal than 15, and you try to find out if any one of these is a factor of 253 or not. You find out that 11 is a factor of 253, therefore 253 is composite. Actually, 253 is equal to 11 times 23.
Example 2.
Determine whether 479 is a prime or not, or composite, okay? Same technique, square root is 21.89, floor function is 21. These are the primes less or equal than 21. Test each one of them to see if any one of them is a factor of 479 or not. You find out that none of them is a factor of 479. Therefore, 479 is a prime number.
Example 3.
Determine whether 1271 is a prime or not. Solution: square root of 1271, square root of 1271 is 35.65. Floor function 35. These are all the primes less or equal than 35. Okay. It so happened that 31 is a factor of 1271, and therefore 1271 is not a prime number, is a composite. Actually, 1271 is 31 times 41.
What is prime factorization?
Writing an integer n greater or equal than 2 as a product of primes. 30, for example, is 2 times 3 times 5. 360 is 2 times 2 times 2 times 3 times 3 times 5. We learned how to do that in 5th and 5th grade and 6th grade. So this can be written at 2 to the power 3, 3 to the power 2 times 5.
Prime factorization theorem, also known as the Fundamental Theorem of Arithmetic.
This is a very important theorem, and let's see what is the theorem, what does the theorem say, and how to prove the theorem. Every integer n greater or equal than 2 is a prime or can be expressed as a product of primes. This is the first part of the theorem, which we are going to proof by strong induction. This is the second part of the theorem. The factorization is unique except for the order of the factors, and we were going to prove this using proof by contradiction. Proof by strong induction. Let Pn be the proposition that n is a prime or can be written as a product of primes. We need to prove that Pn is true for all n greater or equal than 2. Basis step, P2 is true because 2 is a prime number. Inductive step, suppose Pk is true for all integers between 2 and n, and prove Pn plus 1 is true. So, two cases. If n plus 1 is prime, we're done. Nothing to prove. If n plus 1 is composite, then n plus 1 is the product of two numbers, right? And these two numbers are between 2 and less than n plus 1, between 2 and n. By the inductive hypothesis, both a and b are primes or product of primes. Then n plus 1, which is the product of a times b, is a product of primes. To prove the uniqueness, we need the following propositions.
Proposition 1.
Let a, b, c be integers and a is different than 0, then if a divides b and a divides c, then a divides b plus c. If a divides b, then a divides bc. If a divides b and b divides c, then a divides c. And if a divides b and a divides c, then a divides mb plus nc. M and n are integers. The proofs of these properties are very simple, so I'm letting them to you to do on your own. They're really simple, but we're going to be using them in the upcoming propositions.
Proposition 2.
Let a, b, c be positive integers, then if the GCD AB is 1 and a divides bc, then a must divides c. Much divides c. Proof. I can put GCD AB is AS plus BT. That's linear combinations of A and B. That's using Euclid algorithm. So now I'm going to put this is equal to 1 here. I'm going to multiply both sides by c. Now, A divides this term, because A is right here. And A divides BTC because A divides BC. So that's using proposition 1. Then A divides the sum of them because it divides this and divides this, so it divides the sum of them. That's using proposition 1. It's done.
Proposition 3.
If P is a prime and P divides A, the product A1, A2 up to AN, where each AI is an integer, then P divides AI for some I, which means P will divide one of these terms, will be a factor of one of these terms. Okay, so proof by induction. Basis step, n equals 1, there is nothing to prove because if n1 is of one term here and P divides that term, so we're good. Inductive step, assume that if P is a prime and P divides this product, then P divides AI for some I. And let's assume that P divides this product. Now I added one term here, then I need to prove P divides AI for some I. Okay? Two cases. If the GCD of P and this is 1, then by proposition 2, P divides AN plus 1. If the GCD of these two is P, then P divides this product. Since P divides this product, then by the inductive assumption here, hypothesis, then P divides AI for some I between 1 and n.
Proof of the uniqueness of the prime factorization theorem.
proof by contradiction. Suppose n can be written as the product of primes in two different ways. We remove all common primes from the two factorizations we get this here. Now, A divides B1, B2, Bm. Why? Because A times this is equal to B1, B2, Bm. So A divides this, and A1 divides this, and A1 is a prime number. Then by proposition 3, A1 divides some Bi here, and that's impossible because A1 and Bi are prime numbers. No prime divides another prime.
Thank you, and see you soon.
Thank you for watching. More videos to come. Please subscribe.